Okay, to continue with paper 2, just data handling. This next part is a graph that we've already done this year, but if you need some extra help with graphing, I posted for you all to find, it's 11:11. I posted for you guys to find right here. It's one of the more viewed videos on my YouTube channel, but the graphing tips in Cambridge. I can't stand to hear myself talk, but
I can turn anyone into a beach bum.
Hey, real quick, let's go over some graphing tips.
All right, so I made this last year
which
before
is
the
the
exam.
same thing as having it in a
So looking
fraction.
for bar charts, I went over how to make tables and line graphs, what to do, what not to do. Great. So that is for you there in your Google Classroom, so you can find its most recent thing posted. Additionally, something that would be helpful for you guys, if you go all the way down to the bottom, things I posted for you in the beginning of the year. There's the YouTube channel at the bottom. But a couple things. A student learning guide. So just extra things that I've had for you guys for the year. So content. Moving on. Okay. Some examples of the answers for paper 2. What to do, what not to do. But also checklists here and some advice. Things that we've actually done together already. So I always recommend don't work too long, take short periods for breaks. So right here. Practice exam questions, we've done that. Papers from older versions. So this 1, 2, 3, 4, 5, 6, 7, the 8th bullet down will still be useful, which is why I gave you guys the example questions that I knew that should apply. But there's a lot of new content they said they won't be testing. So there is a lack of some practice things, like you saw with the bonding with water and dissolving of salt. Look at mark schemes. You have the mark schemes. You've had it for now about a week. Read all the instructions. Read the questions carefully. Identify your command words, underline them or highlight them. Make sure you know the technical terms of things. Try and rethink what the question's asking. Read all parts of the question. Look carefully for what you're given. Graphs, read a title, read the key. Read the axes to find out what they're showing. The keys are very helpful. The title is helpful. More so the axes, you're going to duplicate the axes identically whenever you do a graph. Try and answer everything. Mathematical terms. Annotated diagrams and a graph can help you, like with tides. You guys saw that too with the water molecule one, which I have that. It was actually kind of a question. It was just almost like 2 marks that I did yesterday, but that was one that we've done at the beginning of the year. Okay. Don't be rewriting the question. They don't need you to. When you're talking about quantities, avoid the term amount. Use the actual scientific term they're talking about. So if it was mass, you might want to say kilograms. Use shorter sentences where possible. Longer sentences can become confusing and lose their meaning. I always say that, you don't need to be writing like it's an English class. Don't be contradicting yourself. You've gone over the list rule a lot of times. Duplicate your axes and your units for a table and on a graph identically. When you're comparing things, remember that you can also find things that are in common as well. Okay, and then so the paper 2 stuff, you guys can read this. So I showed you where you're able to get it. Okay, and again, that's down here in the general. And that was the student learner guide. This is also helpful. Cambridge didn't have this in the other syllabus, which is nice. And when I posted this in beginning of the school year in September, these things weren't here. Just a couple of them were, but like the available experiments were not there. Okay. Investigating the effect of salinity on the freezing point of water might not be a bad one to look at, in case like they do give you a question like that on Friday. And how convenient, the random and systematic sampling that was not there in the beginning of this year, so I had to make my own. Designing tables, which is something you're going to have to do on this sample paper and quite likely on Friday. Designing tables is not something that they've had to do in the past. Drawing graphs, so you have that video, you have the one that I did as well. Biological drawings, planning as scientific investigations, planning as like part 2, evaluating work, and then analyzing data, and then some lab safety things. But yeah, those would definitely be things I would recommend looking at or listening to. I think it'll be super helpful when you're going to have to actually do that on Friday. But that should be no surprise to you because looking at paper 2, you've seen some examples. We'll do this one. Whoops. And then I'll give you another type of question from a different test. I've actually added it to the end from 2014. So if you have to like change an experimental variable. So in this situation, they're seeing the effect of light and the amount of cells that are produced at different temperature. I'm sorry. No, sorry, it's not the effect of light. The light is there, that was standard, but the effect of temperature on the growth of cells, warming temperature, increasing temperature is beneficial because of enzymes. Remember, temperature, we always think about enzymes. And then this question right here, it might seem intimidating, but they're actually quite simple. So if you're asked to have to change an experimental variable, so it says something other than salinity. Nope. Sorry. They did temperature, and they said, okay, there other factors can affect it, including salinity. Design one where you would do salinity on the growth of that algal species. And so you reference the control variable, so things you're going to keep the same, collection of quantitative results, quantities, numbers. So how you're going to collect your data, your numbers. Literally, what in easy sense, you're just going to do the same thing that they did right here, but you're going to do different salinities. And you don't need to assume like the number of cells that they're going to create. You would just say like you would measure them, and you're going to literally measure them the same way that they measured as well. So that's I'll run through that question with you as well. Moving on to this one, we've already done it before. I inserted this here too, so this should be familiar to you. We did this in the beginning of the year whenever I taught you the basics of graphing. I'm not going to go over it again. You guys have it available, and then you also have an additional video for me. So it's just I don't want to waste anyone's time because you have that information somewhere else. All right. Something to consider though, you don't include units in the body of the table. You're only going to include your units in the column heading of the table. Always use a ruler whenever you're drawing it, and definitely use a pencil. All right. I'm going to yawn. Okay. I'll show you an example. Yeah, here. So the number of cells in cubic centimeters, none of these said cubic centimeters here. So you just have it in the column heading. Okay, so looking at the temperature, how temperature affects the density of pure water. Plot a line graph, so it already tells you. And like I've said in the other videos as well, if a graph is seeming to be very difficult for you, you might be doing the wrong one. It seems impossible whenever you're doing, if a bar graph is becoming impossible to do because for whatever reason, it might be a line graph. So consider like if you have two sets of quantitative data. So numerical, we're going to do a line graph. Bar graphs are for categories, essentially. Something to remember though, if you are doing a bar graph, and this is where I would like use the pencil, and I demonstrated this for you. Literally, if you have to fit in 5 different categories, with my pencil, I make sure like, okay, I can put a bar here, and I have to skip one, and just make sure I can plan it out. Bar here, skip one, bar here, skip one, bar here, skip one, bar here. You want to use at least half the space or more, line graph too, and you cannot have your bars touching. They could be separated just by like one box if that's the way that you planned it. And it has to be drawn with the ruler or you're going to lose marks for that. So you could separate it just by one box, but in a bar graph, they can't be touching at all. They can touch the axis, but they can't touch each other. And they do need to be equally spaced apart, which is where you'll get marks for like being able to plan it. All of those little details I go over in that supplemental video that I've had on there for like a year now. And if you want to like look over what you did in the beginning of the year with like these notes, go for it. Okay, so plot a line graph and use a ruler to join your points with a straight line. So this is your X, this is your Y. Y is a long tail, so it's going to be your X. Your X is what you are changing. It's what your manipulated variable is. It's also called the independent variable. So I taught you the term dry mix, or the acronym rather. Your manipulated variable is what you're changing. If you're manipulating something, you're trying to change it. And then independent is the independent variable, and it's on the x-axis. So if this is like, I want to see the effect of salinity. I want to see the effect of light intensity, the effect of temperature, the effect of density on whatever. The amount of fish in an area, the amount of larval species, how often corals will come out of their polyps or out of their, their coral, the coral polyps will come out of their calcium carbonate shell to feed. And then the dependent responding variable, and if you're giving a response, that's like the answer, it's what you are measuring, is going to go on the y-axis. So you wanted to see maybe what the effect of temperature does to density of water. What you're changing is temperature, and then what your response is going to be density, and they're measuring it in kilograms per cubic meter. Okay, first thing you should do is label your axes. You should never have to wonder because they're already given to you. And that's one of your marks, is to have identical labeling. And you are not going to highlight, obviously. You're never going to highlight your own graph. You can highlight a graph that's made for you that you have to analyze. Don't just put temp. Don't just put temperature. It's temperature of water, and it's in degrees Celsius. Okay. This one is density in kilograms per cubic meter. You can write it like that. I always say in class, I'm more of a fan of this because that's how you're figuring out density. It's mass per volume. It's the formula for it. So this is the mass, this is the volume. I just prefer to see units in like the mathematical, like it's mathematical way, I guess. Okay, and then you want to analyze like the numbers that you're given so you can start to make a suitable scale. And no matter what, you're going to have a 0 down here. If you don't have a 0 at the origin, we've already gone over this, but if you don't have a 0 at the origin, then the scale is going to be wrong automatically, unfortunately. But that's the rule. Okay. All right, my numbers go up to 50, so I could do 10, 20, 30, 40, 50. Okay, and that's what I'm going to do then. Watch what you're counting by, because you're graded on the scale. The scale 1 has to be like counting in the correct increments. So if you're saying like, if you're putting 10 here and then you go 20, automatically like that's going to be incorrect. Because if you're saying the space right here, these 5 boxes are worth 10, but then you're going, these 10 boxes are also worth 10 because you're jumping from 10 to 20, that's not going to be something you get a mark for. So make sure you're counting in correct increments. Additionally, you don't want to go like 25, 50 for a couple reasons. One, now max your graph is only going to be like right here. It'll go this way. And then like this is the maximum space that you'd be using. You're not going to get marks for that. You also don't want to cause yourself to be like, okay, well, I have 10 boxes here, and then I say that's 25. So 25 divided by 10, cool. Each box equals 2.5. That's, why do you want to count by 2.5s? If you have to, you have to. And, as long as you're using half the space or more and you're counting in correct increments, they're not going to take that mark away, but you have to count by 2.5s. Be good to yourself. All right, I'm going to do 10, 20, 30, 40, and 50. I know this is obvious, but a way to just assist yourself a little bit, I'll look and say like, all right, this is, I got my numbers to fit, but I have 10 boxes and then I get to the number 10. So I know that each box will be worth 1 then. Likewise, if it was these 10 boxes and this number was 20, then I would say, all right, I got going up to the number 20 and I have 10 boxes. So, the value is 20. I'm splitting it 10 ways. Each box will be worth 2. And then you don't have to do that. I don't see why you wouldn't want to. So then when you are trying to put your numbers in, your values, and you're actually graphing it, you're going to have some more direction for yourself. All right, so focusing on density, you're going from 988 up to 1,000. Fun. Analyzing this just real quick, so that's a difference of 4, another difference of 4, difference of 2, difference of 1, difference of 1. Okay, so that is actually, looking at that's kind of going to allow me to think like, how far do I need to jump, essentially? How many lines can I have in between? But you're not going to essentially maintain this starting point at 0, because you're not going to include, like, you're going to put a break in the graph. You're not going to include, any number, honestly, in between 0 and like 980. Like, why would you? Then you'd have a big empty graph. So the way that I've showed you to do that, which you've seen, I'm sure, in other classes or another graph, you're going to break the line, break the graph. I think another way I've seen it is people do this. I'm just not, it's just not one that I'm as familiar with. Not that I'm familiar, I just don't use it. I think it's doing that. It's another way to break the graph. But they'll look for one of those symbols, either to do this or this line. And so that just tells them that you're not going to be maintaining those. Like you're not counting by that. You're like skipping a whole bunch in between. Like if this was an accordion and you like pulled it out. Okay. What if I did 980? Rather, let's see, 980, 985, 990, 995, 1,000. Ooh, that'll put me right in the middle. Not a huge fan of that. It's not wrong, but I'm just not a huge fan of that. Okay. Do this in pencil as well, always. Okay, I'm going to double check that I have the same amount of space in between. So here's my break in the graph. So I'm saying this is the 980. I'm skipping 10, I go to 985. I'm skipping 10, I go to 990. 995, skipping 10, and then 1,000. All right, and then just so I remember what I'm going to be counting by, like what each box is worth, because remember you can only make half of a box mistake. I'm going up a value of 5, so 980 to 985. Going up a value of 5, I'm splitting it up 10 times. Each box, not 0.2, 0.5. All right, then I always check, so half, 1, half, 2, 3, 4, and 5. Okay, yeah. Great, great. Not 0.2, 0.5. And now I have those there. Now I'm going to graph. I'll do it in the blue because you can use blue or black pen. Never use different colors on here. I'm only doing that just so you can see the different areas. All right, so 4 and 1,000. Each box down here was worth 1. So here's 4 and 1,000. Okay, right away there's a problem. You can't do a dot and a line graph. You can do an X. You can do a plus. If you're doing dots, you need to put a circle around it. And with that, the circle cannot be super big. So if this is your point you wanted to do, the circle needs to be within the 4 squares around it. You would not want to do this. That's covering too much. And that would go same for like your X. If that's the point, that's where you're going to put it. You don't want to do this. $10 and then $9.99. So it's 1,000 and then half. Right, 20 and $9.98. Right, 99 and a half, 98. 30, 996. 40, 992. There's my half. So 85, 86, 87 and a half, 88. Okay, now I'm going to join it with a ruler. I don't have a ruler in here. Things to not do. Sometimes, like when you just don't know better. Oh, hold on, let me draw my line in first, and then I'll talk that part out. You're going to connect them together. You're not doing a line of best fit, so you're not going to try and like put your own line in between here. You are making the curve. You are connecting it. Connecting each points. And this one here is even like a little crooked. All right. So now it's more, I mean, it was obvious in the data table, but it is it is obvious now, visually obvious, that we can see that as temperature is increasing, that the density starts to go down. That's a negative correlation. What was I gonna say? Oh yeah. If you don't know better, you might want to do this or something because like, you might think that it looks incomplete. Don't do that. That's called extrapolating. Unless you're told to extrapolate, which I don't imagine you will be, but like, or to extend the data. If you're not told to extrapolate, don't extrapolate. Excuse me. You don't have data for 55 degrees. You don't have data for 57.5 degrees. Sorry, not 57.5, 58.5 degrees. So don't assume it. It doesn't make it more complete. It actually makes it wrong. All right, so I have my scale correct. So that's going to be 1 mark. I labeled it identically to the data tables. That's the 2nd mark. My points are in the correct area. That is the 3rd mark. And then I did connect them with the rulers, your 4th mark. And not just connecting with the ruler, but I have like the correct, sorry, the correct type of points on there. They're not dots. They are a dot with a circle or an X or a plus. Use data. So there's a command. To describe the pattern shown by your graph. Okay, and we've done examples like this before too. Anytime they want you to say describe the pattern or describe the relationship, you're going to say the same sentence, and you've written this down this year. Oops. As the title of your x-axis does whatever it does, or maybe it stays the same. The title of your y-axis does whatever it does, or maybe it stays the same. And if they want you to use data, then you're going to use data as an example. Like, and not necessarily as an example, but like to support. Okay. As my x is temperature, I'm going to put temp, but you guys don't. And then what are these numbers doing? They're going from 4, 10, 20, 30, 40, they're increasing. So temperature of water increases. Don't use arrows on your test. The density, 1,099, 98, 96, 92, 88. That's going down. That starts to decrease. So there's 1 mark. This is worth 3. If you have a data table and maybe it's like 1,000, 999, 998, 1,000, 1,001. So you would say, like, as the temperature starts to increase, the density decreases, but it doesn't continue to decrease until 30 degrees, and I'm just using this as an example, 30 degrees Celsius, and the temperature increases again, or until 20 degrees Celsius. And then at 30 degrees Celsius, just based on where I have this right here, it starts to increase again. And then, whatever happened down here, maybe it stayed. And you would say then it remains constant, stays the same, doesn't change. But follow your numbers. If they're going up, going down, going up, then you're going to say it goes up, and then it goes down, and then it goes back up. Maybe it plateaus, stays the same. All right. So to get the other 2 marks that are on there, something that we do notice, there's an area in here that has a greater slope. I'm going to use the ruler or the highlighter to identify it. Here, the slope isn't as great, and hopefully you can see it without having to actually do a change in X over change over Y kind of situation. But then right here, at like 30, the density goes down pretty fast. So this area right here. So a way we can say that, or just discuss that kind of data is, or the way that it's represented is that there is a greater decrease of density at higher temperatures. And I know higher is relative. You can get, which, you might feel like, it's not that like specific, and I tend to agree. But you could say, at 30 degrees Celsius, as the temperature increases, the density falls faster. That is another thing you can talk about. You might get away with saying there's a negative correlation. So the density increases, which I don't really like that saying. You could maybe say the rate, change over time. The rate of density decrease increases, or density decreases faster as temperature increases. The rate of density decrease increases as temperature increases. Past 30 degrees Celsius. And then it says in the mark scheme, manipulation of figures, data figures. Sometimes it says manipulation of data. That is not something you can write on a test. You don't put manipulation of data. Okay, well then manipulate it. Like, use your numbers. For example, we can say between, it doesn't matter what you choose. It does not at all, as long as it's supporting the description, or like the relationship between your data. So whatever data you use, and it's going to come from that table, it has to support that. As temperature of water increases, the density decreases. It has to support it. So we can say like between 4 and 30 degrees Celsius, or 4 and 40, or 10 and 40, 10 and 50. It literally doesn't matter. I'm just choosing those. The density decreases by 1,000 to 96 is 4. And what are you measuring it with? Kilograms per cubic meter. Okay, so to manipulate a figure, you're just gonna, like, I think the easiest thing to do is just like find the difference and subtract. That is the simplest. So like, if you're trying to show that as something increases, something else is increasing, or something decreases because of it, then like prove it. Well, okay, it's temperature increased, 4 to whatever you want to do, 10 to whatever you want to do, 20, and then correlate that same data with that temperature. Use that as your response. Don't say that on your test, but between 4 and 10, 4 and 30. So aside from the graphing skill, to get this bottom part right, you're going to refer back to what I taught you guys in the beginning of the year, that this sentence for state, this is for always for state the relationship or describe the data, describe the pattern, and then do some takeaways, do some subtraction if you need to compare them. Describe, so what, and explain why. How you would expect the density of pure water to change as it goes from 4 to 0 degrees Celsius. Key thing here, they're talking about ice. It's pure water. 0 degrees Celsius is its freezing point. And as I mentioned on paper 1's lecture video, water is the only solid molecule that will float on its liquid state. All right. I'm going to pull through Google Classroom really quick so you can see what I'm referring to. There's your test answer. I think this is textbook. Okay. All right, so it's because of the hydrogen bonding that causes it to be less dense. And this is like right here what the question was talking about today. Why does water bond with itself? Okay. And so the answer for this test question is actually where it says density. As the temperature decreases, the kinetic energy decreases, causing molecules to move slower and closer together. But your hydrogen bonds are going to grow stronger now. Those hydrogen bonds will almost like push away from each other because of the electrons there. And so the solid lattice that it's actually going to form will push those water molecules further. And it's because like the kinetic energy, the energy of motion is pretty slow. It's not like ice slips past itself. It's like water can. Like water can make things slippery. The kinetic energy is really high. And the notes that I gave you guys, when the kinetic energy is really low, and that's literally what low temperature means. Temperature is the measure of kinetic energy of something, so the measure of like the particle motion of something. As the temperature starts to go down, the movement of the water molecules are going to go down, and this means that like now like they kind of almost start to line up, and I've showed you this in a video. They start to line up and they are almost like repelling each other. They're able to repel each other and keep each other almost like in the lattice structure instead of them getting so close. They're repelling each other because you have areas that like partial negative is not going to attract to a partial negative. Partial positive is not going to go to a partial positive. They're going to attract to their opposite charges, but the repulsion like keeps each other like in this lattice structure that you see I drew out for you right there. Oh, excuse me. And then more about hydrogen bonding. Okay. There's your salts in the ocean question. Sodium chloride, calcium carbonate, magnesium sulfide. That's never been a question on there before, but now I know. And I never would have anticipated that either. Okay, so the density will decrease, and your reason for that, because they keep each other like at a distance. All right, depends on. If you're interested in seeing that again, it's one of these. It's how does water bond? There we go. It's this YouTube video right here, right there. It's 1, 2, 3, 4, 5 down. Describe and explain how data from samples of seawater would differ from the data of pure water shown in table 2.2. Okay, well, here's your data in 2.2, 2.1. There's no 2.2 yet. So describe and explain. So what and why, how the data for samples of seawater, difference between seawater and pure water is seawater has more dissolved solids in it, higher salinity. How would that differ from data for pure water in this table? So no matter the temperature, it doesn't matter. Water of the same quantity, like the same amount, the same volume of water, if you put salts in it, dissolved salts, it's going to increase its density. So at every single temperature, it doesn't matter, the salt water is going to have a higher density overall because it's not just H2O, it's H2O plus NaCl, CaCO3, magnesium, and sulfate. Don't use the word temp. Okay. Dissolved salts or higher salinity adds to the mass per, or you could do like the slash. And density is kilogram and then volume, mass and then volume. So the dissolved salt or the salinity is going to add to the mass per volume of the water. I bet because they don't say describe and explain how data of samples of seawater would differ. Like, yeah, I imagine you could get away if you didn't say mass per volume. I know it like seems a little bit wordy, because that is like the formula for it. Density is mass over volume. I bet you could probably get away with saying density because it's not directly in the question. You're not going to get one of those like buzzword marks, like, oh, you use terminology correctly, if you're essentially just repeating what's in the question. All right, so use your data in table 2.1. Explain which is why, the role of density in the formation of temperature layers in the ocean. So we think about like, what is that meaning? So density in the formation of temperature layers. So let's consider why there's different temperature layers And what does density, what's its role in that situation? What does density have to do with that? How does density form different temperature layers? Don't let a wordy question make you feel dumb. Easier said than done, I know, but it's try and reword it. And in this, you don't actually, they're not like calling for you to actually use the data to get full marks. It might just like use the data to help you, but I don't know. Use the data to explain the role of the formation of temperature layers in the ocean. So here's depth, right? Here's your seabed, surface. Okay. Actually, I'll do this one. Sun. Sun adds energy, solar energy, and thermal energy to the surface. So you got that warm layer at the top. Then we lose its temperature pretty quick. Colder water at the bottom. Warm water at the top. And then once you kind of lose all that heat from the sun, the temperature falls really fast. Then it continues to fall slowly towards the bottom of the ocean. Can't touch the x-axis. In this area, be the thermocline. All right, and why is warm water at the top? If you answer out loud, good for you. Good for you. Warm water at the top. It's less dense because it's got a lot of kinetic energy, which is like kind of ironic for, not ironic, but almost contradictory of why frozen water, ice, will float. But there's like a threshold there for your hydrogen bonds. You got the thermocline, and then we have colder, or yeah, cold water sinks. It's more dense, but it's like once it gets that frozen state, it's like the hydrogen bonds like lock in with each other, and hydrogen bonds are actually relatively weak. So adding temperature to it can change its state. That's the like kinetic energy thing, the kinetic energy theory. You'd have a form here, you'd have another one form here, another one form here. So it starts to make like a lattice structure. So I'm going to take that and I'm going to use it as an answer. Parentheses mean that parentheses are more for direction for you and elaboration than that is a part of the actual answer. Water is warmer at the surface due to the sun, causing it to float. So, easier answer, I think, than trying to decipher through the question, but explain. So it's why. And so we said why. Why? Because it's higher density and it sinks. Water, and water is warmer at the surface. It's floating. Colder water is going to have higher density. It's going to sink. Essentially stating that you could also say that warmer water has lower density. It's going to float at the surface, and then colder water is going to sink. You really only need to mention like that density correlation with it, at least with one of those temperatures, because then if cold water is higher density, then it's the reverse argument essentially that warmer water is going to have lower density. Yep, and then how it forms temperature layers. Okay, I'll do this one more time, but I'm not going to give as much elaboration on it because you do have the other video that goes along with this. That is the mark and recapture video. It's the first one. Okay, so blue striped snapper, there's its species or scientific name. These fish were introduced to Hawaiian Islands. Their numbers have gradually increased. Scientists have used a mark and release method to estimate the population of blue striped snapper. Oh, excuse me. Scientists use nets to catch the fish, and then they mark the fish with a harmless tag. They said harmless, and it was attached to their fins. The fish were then released, and a second sample was caught 2 weeks later. So remember, there has to be like a certain time frame in between. The number of fish that were in the first sample and had the mark was 52. Something that changed too is in the other syllabus, they called, instead of M2, they called it like N3. Anyway, they're going to give you these formula though. After those 2 weeks, they go back, and the fish that were caught in the second sample, 41. Total fish, number of fish, both marked and unmarked, in the second sample. And then within the second sample, 12 of them had the original mark. So marked individuals that were recaptured, and they found them in the second sample. Okay, so now we're going to do the math. Calculate the population size. Say your answer to 3 significant figures. N is commonly population size. I don't know why, but I know why, because it means number, like the number of individuals. So even like in ecology or like biological sampling, population sampling, obviously. Put too many X's. Like 8. So you're going to get 177.67, but that is 5 significant figures, and they only want 3. Another thing to consider is they're answering to you in whole numbers, 52, 41, 12. You should also be giving a whole number. Okay. So even if you rounded this to like 177.7, rounded that up, now you have 4 significant figures. And this right here will get you just 1 mark. But to get it in 3 significant figures, you're gonna just round it up again to 3 numbers. And this mark scheme isn't like specifying to put an or like a unit on there, which makes me not trust it. So I would put a unit on there. It does say calculate the total population size. So 178, and they are blue striped snapper. Okay, discuss the factors that should be considered when collecting the sample so that the accurate estimate of the population size of blue stripe snapper is obtained. I believe, and I don't know because I don't know the exact question, but I feel like you had a question very similar to this about the dorsal fin with taking the pictures of them today. And it was like discuss the limits. And I did emphasize that in class that that is something that is different on the syllabus, and it is something that I took time to go over without any interruptions. So it was screen recorded without you having to be out for other Cambridge exams, other testing, field trips, asking somebody to go to the bathroom, falling asleep, interrupting class with falling asleep, because it is very distracting to me. It's hard not to watch somebody like nod out. It's weird. It's very strange. Okay. Cell phone stuff, like it's just other distractions, which like negates the lesson for everybody else. So it's much more efficient doing it this way. Except now we have like little Olive interrupting, but we'll deal. All right. So things that you should be considered. Oh, and then here's the limitation one. Okay, so to make it more accurate, because they said they want an accurate estimate of the populate size. So things that you want to consider whenever you're going there, like literally going there to sample the snapper. Think about like where you're going, right? Where you went the first time should definitely be where you go the second time. Sample from the same place on the reef. Additionally, sample at the same time of day. And that matters. Like, you don't want to go, maybe if you went early in the morning one time, you don't want to go at like 11 o'clock or around noon the next time. Maybe there's like boats out or people are kayaking or something, and so maybe the fish will hide. Tidal cycle. So sample during the same PT point in a tidal cycle. Okay, so if you went at high tide one day, then when you go again, go at high tide again. Don't go at low tide. Even though this is a reef, it's not like an intertidal area, but your water currents will play a bit of a factor in that. And you don't want anything to, place an inaccuracy on the values. Okay, same, I wouldn't have thought of this, but same catch effort. Now I will think of it because I realize that is a possible answer, and literally this is I think the best way to learn is through practice of the mark scheme. But this question and then also the limit question are new to the syllabus. So use the same catch effort on each sample or each sample day. So if like 3 people are trying to sample fish the first day, and then you go out 2 weeks later, it was 2 weeks, right? Yeah, 2 weeks later, and now it's you and 4 people, 4 other people, so now there's 5 helping. Ideally you're going to catch more fish a second time, so you're just going to now grab a bigger population sample. If it was just you and you got a sample one time, and then I don't know, you did like heavy workouts or something, or you do pole vault, who knows? Then 2 weeks later you go and it was maybe right after you did an exercise and your arms are sore. Maybe you don't want to be using the net so much, and so on purpose you're not like going to go out of your way to try so hard to catch a ton of them. Okay. So some kind of reference or statement about sampling, or rather take samples. Should be taken with an appropriate length of time. So for these fish, it probably isn't going to make a big difference, like that 2 weeks. So it will make a difference, but that 2 weeks, a year, no. If they're migratory, or maybe they, go places during like migratory, they're migrating like different seasons. Maybe they need to go somewhere else when the temperature changes. Excuse me. That would be something you want to consider. Likewise, if you were trying to sample larvae species and then like use like a sieve and filter like zooplankton from the water, I've included like a picture description of what that looks like on your 3.2 notes whenever it was talking about measuring biomass. So counting the amount of plankton in each and like the water sample that you collect. They are microscopic, so there are different types of like microscopic filters that you can put it through. So you wouldn't want to wait if you're trying to sample plankton species. You wouldn't want to wait until like, a couple months, because after 8 weeks they'll change their larval form. A lot of species that do spend their larval time as plankton or free floating in the ocean are gonna, most likely be out of that larval form or pretty close to it. And then ensure tags are attached the same way. So you and whoever you're working with will need to make sure that you're doing the same type of method to attach the tags, because if a tag falls off, well, if you give them a tag and now that's part of your N1 sample, then you grab your next sample, and let's say like of 3 of the fish, 3 tags fell off. Well, in that N2 sample, the second one, ideally there should be like fish in there, right? With what I say, 3 fish had the tag fall off. There's 3 in there now without a tag, and it looks like maybe your population is going to be bigger than what it actually is. Because then it seems like you haven't accounted for them already, but you have. So where like this number, let's say that number should be 15, and then 3 tags fall off, well, now it's 12. So now you're dividing by a smaller number. When you divide by a small number, it's going to make your total answer much bigger. Okay. And that is actually something we could say right here. So describe, so what, and explain why. One limitation when using the Lincoln Index, which is the type name of that, the mark and recapture formula, to estimate a population size. Tag could come off. This would make the M2 value smaller. Population will end up looking lower. Here, I'll write it for you. What they call it, M2? Yeah, the ones that are marked in the second sample. N2 is total in the second sample. M2 is within that second sample. How many had that original mark? You could have fish entering or leaving between your sampling days. And that one they said 2 weeks. So you could have fish that are coming or going. And so this would ultimately cause this in the second sample. It could be larger than it really is. Or likewise, it could be smaller. Or if some of the fish that are leaving, right, already had a tag, this could cause it to be smaller. If they already had a tag and they left, because you originally, the ones in M2, you originally caught them in the first sample. Put a tag on them, great, let them do their thing. N2 is, let me grab my second sample then, and then how many already had that mark. So N2 could be larger, and that's if they are entering. Or for the same one, you could say if they're leaving, N2 and the M2 could be smaller. I don't want you guys to say and because you could contradict yourself, but I'm just saying for like the sake of this, both of those things could end up looking smaller. He would just have to say one of them. And what if your original sample size, the first time that you went there, what if that's too small? What if you only sampled like 15 fish? But really in that area, maybe they can like be in shoals up to like 200 or something, but you only grab 15. So let's see. This could cause just a greater room for estimate error. Okay. Nice. All right. So we went over graphing, that density, temperature, floating, little thermocline stuff, sampling again. It's already done. We'll do that one. But first I'll do this one too. This one's pretty simple. The word equation for photosynthesis, even if you don't do the word equation and you just do the actual formula, if it's balanced or not balanced, it doesn't matter. You'll get full marks. So I'll do both. I think it's actually more difficult to just write it out in words and not the balance. But okay, so plants need water and carbon dioxide. Remember, when there's too much CO2 in the water, it creates H2CO3, carbonic acid. Can dissolve shells. Okay, and in the presence of sunlight, yields isn't necessary for this question, and it's not gonna make it incorrect, but sometimes you'll see it says chlorophyll or like light because plants need chlorophyll to absorb the light, but they will yield oxygen, and they synthesize glucose, organic material. And to balance it, 6 waters, 6 carbon dioxides, 6 oxygens, C6H12O6. But you just need the word equation. Okay, got it, dissolved, got it, and cool. All right. Okay, this is one we're definitely going to want to use highlighters for. So blue striped snapper are host to 2 types of parasites, A and B. You had a parasite question today. I believe it's like copepod and then something else. Samples of fish were caught each year for 8 years. You see it here, 2001, 2, 3, 4, 5, 6, 7, and 8. They were examined to identify whether they were carrying either a parasite, and an assessment of their overall health was made. Okay, and if we look over here, you can see they're measuring percentage of fish that are carrying the parasite. So there's 2 different kinds, A and B, and that's what you're going to be measuring that on. And then on the other y-axis, because the values aren't going to be the same, where they're measuring 0, 20, 40, 60, 80, 100, because it's percent, or like what portion. The health index, they said the assessment of their health was made. The overall health was expressed as a healthy index, where a higher number indicated poor health. All right, and so the health index is right here. All right, and even, like if you have to see a double axis like that, just, it's, if you're like, what am I supposed to read? Like, it's telling you the what it's labeled is what it is. And the answers are always in the text above it. And yeah, right all over it too. Okay, so this figure shows the percent, or the portion of fish that were examined that carried each type of parasite, and then their mean or their average health index of the fish each year for those 8 years. So the amount, or the portion, right? So out of all of the ones that they got, like in 2001, counting by 2s here, so like 16% of the fish that they sampled, the blue striped snapper, 16% of them had parasite B. And if I read across, they were in good health. Where parasite A, 54% of the snapper then had parasite A. In 2001, parasite A, they were in like medium health, like moderate, not the best. Okay, and so sometimes, like, and yeah, not sometimes, often I'll say, before you read the question, like, try and make sense of the data first, because that can almost like compound it. Okay, I'm gonna just highlight the health index to match the axis that they're measuring it with, the data, their values are measuring it with. And then this can help you just kind of see it pop out and see the correlation better. So you have a baseline here in 2001 and their health index 10. So this is like middle, 5 is middle, it's poor. So it was in a relatively good range. And then in 2002, you see a spike. And then 2003, it goes down. 2004, they get worse, they get sicker. And then it'll go down. 2005, it goes down. Healthier, sicker, healthier, sicker. Because we know that poor health is a higher value. All right, and then I'll do it for parasite A and parasite B. Nope. Okay, so it looks like there's a little bit of some overlap there. And parasite B. And in those years here, 2010 to 2003, parasite B increased more compared to like their population increased more than parasite A did. However, there still weren't that many fish that had parasite B. It's still like lower than A. Like, because we're looking at the percent that are carrying that type of parasite. It's like 2003, but 40, 38, 36% had parasite B, while 62, 64, 60, like 68 of fish had parasite A. And then their health index was not ideal. It wasn't the worst. All right. And so the question to answer with reference use examples from the graph. Discuss the extent. Extent is going to mean limit. Similar thing, like how far do you agree? Discuss the extent to which the data supports the hypothesis. So in this question, you want to say it supports it in the following way, or for example, in this year, blah, blah, blah. And the hypothesis is that parasites decrease the health of the blue striped snapper. So where in the data does that agree? And is that always going to be true? Okay, so I want to look for places like maybe where that is going to be consistent, but also places where maybe it's not always going to apply, right? Maybe it's going to be different for parasite A versus parasite B. For example, I kind of see one right here. Like they don't perfectly follow each other. Like here, between 2005 and 2006, they stayed at 30%. However, if I look at the health index in 2005, it was just under 7. So not ideal, where if this is like middle bad and this is like very bad up at 10. 6 is not, yeah, a little past 6, almost 7. Not ideal. And then again, 2005, 2006, parasite B stayed the same. Its population didn't change inside the percent of fish that carried it. It didn't change. However, 2006, the health index went down, which means that their health improved. And putting that, like those little notes here, good health, poor health, that'll be helpful. Because I feel like sometimes we look at like, oh, it's a 10. We're like, that's a good thing. But it really depends on what they're calling it. Their health improved. But you didn't have any sort of change on the parasites in between 2005 2006 of parasite B. You did have, though, a big decrease from 60, and just so you can see like what they're counting by, like there's goes from 0 to 20. You got 10 boxes in between. Each box can be worth 2. Okay, where's that? Likewise, 2005, parasite A was at 80%. And then in 2006, that's 50%. And this is 50, it's right under it, so 48. Parasite A is at 48%. So that can support it there. That can support it there, but does it always support it there? Because then if you go from 2006 to 2007, parasite B increases. And their health index goes down. But yet it didn't cause the big issue for 2005, 2006. Over here, we have an increase from 20, so 16%. Notice they did X's for their dots. And here, 40, 38, so that's 36. So it increased by 20%. The amount of fish that carry parasite B. There was an increase between 2001 2003. But the health index didn't do that trend. It wasn't until 2002, and the health index, what is this one over here? Like a 4, just under a 4. The health index was pretty good. They were healthy. And then even though we had this like continual increase in parasite B, you didn't see this health index do this. So you had a very small increase in poor health, very small though right here. And then in 2002, even though there wasn't that kind of like change right here in parasite B, it maintained it from 2001. In 2002, the health index goes from being relatively healthy, spiking up it's past like your middle bad, I guess I'll call it that, where 0 is good health and 10 is poor health. So it's going past that 5. Right here. You have a big increase, so they're getting sicker. But nothing changed in parasite B necessarily. Like it had that constant increase. And parasite A, there was an increase here from 54 to 64%. So you would change 10% change in that year. And then you go from 64 over to 68. So there's a 4% change. But so why this huge like skyrocket in bad health on your health index? So the limit to which it does support, and we do want to use some data, we can answer that a little bit. And you want to use examples, kind of like that's why I marked all over it, gave some dates. Places it does support. Places it does support. Places where it's peaking. So 2007, high parasite in A, sad health. Okay, we have this increase right here, that parasite B or green line from 2004 2005. You also have an increase in parasite A, 2004 2005. Poor health right here. Likewise, that 2001 or the 2002 to 2003 increase also correlated to poor health. So we can write that. And the way we can say that is the years that the health index was high, or you could say they were in poor health. There were also higher parasite numbers, parasite percent, parasite numbers. And a second mark for this, and you would maybe put this actually in that first mark. If you said the years that the health index was high, they were also high, like both parasite numbers were high. If you said both, then you would get 2 marks right there. In 2006, the health index was low, but parasite B numbers were high. So we show that. So health index went down, but so they got better. They were improved. This blue line, they improved. It's the smiley face. But you didn't see a change in the parasite B. So like, are they just spiking together, but their decrease doesn't fall at the same time? Right? Because typically when you see like their health index getting really bad, which is at these peaks, you also see the parasites peaking. But in 2006, the alternative wasn't true. You see their health index improving, but you didn't see an improvement in parasite B. So this would be like How far does it support the hypothesis? Hey, Sophie. Or 30% occurrence. And this one right here, this weird one, let me erase a little bit of it. Oops. I got you, Soph. So another one to consider is 2007. Your health index was high, which means sad face. They're getting sick. But this is the first time, really, in the graph, something like to notice, and sometimes these things are going to pop out at you until you kind of like pick apart these numbers and like kind of put a story to it, like I just did. Throughout this time, you've seen that there was like when they're sick, right? When there's this blue line is spiking, A was high. Here it's spiking, A is high. Over here, you got spiking, so they're sick, but A is lower than it. That population is was not that high, and comparatively, the population, or sorry, not the population, but the percent for parasite A in 2007, it's right above that dark line. What is that dark line? Dark line is 60, so 62%. That's like actually it's 60%, right? 60. Anyway, that is like its lowest peak on here. 61. Ugh. That is its lowest like high point. There it peaked. But the peak over here was 80 in 2005. The peak in 2003 was 68. It's like baby tiny peak in 2002 was 64. And here it's 61. So that will be one more thing that is that you might not agree with or might not use to support it. The fish were in poor health. Or not as high as they have been. And like these are the types of questions where, I mean, you just saw me pick through it. And before I even like wanted like to even reference the mark scheme, honestly, even before I want to like read the question, I do this with a lot of graphs. And sometimes I waste my time and I am just analyzing it too much and the question like doesn't even really require me to analyze it that much. But I try to like tell a story with it in my head, or like you see an increase in it. What is that increase meaning? What happened there? And then, look at the smaller details. Well, is it increasing in relation to anything else? It's, helpful that I like kind of give myself a key on the side and keep telling myself, wait, if this number is increasing, that's actually not a good thing. That means that they're getting sick. Those are good things for you guys to do as well. Kind of have the graph tell you a story. One more thing we can put here is this idea that causation Causation. Bless my heart. Causation. So the cause of something is not going to necessarily mean that it's going to correlate, vice versa. Correlation, not causation. Things may correlate, and that's actually what I'm going to write instead, and then I need to like put myself to bed. Correlation. You may have correlations, highs and lows, 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 but are they the cause of each other? So correlation, just because things correlate, does not mean it's the cause. Correlation is not causation. Here's an example. In 2020, that was probably one of the, in the past 50 years, one of the times that toilet paper sales were through the roof, right? You couldn't keep them on the shelves. It also happened to be a year where we had a ton of students learning at home, almost everywhere for a while. So was the toilet paper being taken up by all the students at home? The numbers will support it, for sure. Yeah, the numbers support it. This year, we have more seniors not eligible to graduate due to low grades. And this is true. And this year, there's every day there are more casualties of the civilians in the Ukraine. So are seniors failing because of the increase in casualties in the war in Ukraine? No. So they can correlate. They might look like they're making sense, but it's not the cause of each other. They don't cause one or the other. This is a question that you want to get your 3 marks on it. You're going to take the time to kind of pick out the numbers. And because it has 3 things moving, right, that might seem confusing. And it really would be. In class, I rarely, never, will just look at a graph without putting some sort of color to it or something, because it's just not as functional for us. It's not as helpful to see. I recommend you do the same. So I was telling you I would bring at least 2, 3 highlighters, right? This will take you a little bit longer than 3 minutes to be like, wait, so this happened, this happened, this happened, this happened. Write some data down. If you want to get full marks on it, you'll take the time to do that well and to kind of analyze it, but it will take you longer than 3 minutes. So questions where you're going to throw in a quick definition, questions where you're just going to state something really fast. Those are the things that I've pushed you to know and save your time on for sure. All right, guys, that's it for me, and I will see you tomorrow. Because I just did all this right now, I imagine I will definitely be building this in class with you. Have a good night.